Hi guys. Today we're going to take a look at the first part of the CP Chem Chemistry of Acids and Bases review sheet. We're going to take a look at the answers, take a look at why the answers are what they are, and then in part 2 of this video we are going to take a look at the rest of the sheet, which so today, the first part, we're going to deal with acid-base theory, acid-base properties. We're going to take a look at pH and POH, and then strong versus weak acids and bases. Then in part 2, we'll take a look at acid-base nomenclature and formula writing, along with acid-base reactions. And then that should get us ready for our test on Tuesday the 14th. All right, so let's take a look from the very beginning, and you'll find that this goes in almost exactly the same order that the lessons went in over the past couple of weeks. The week, before we got out for spring break, and then this past week. So let's take a look at the very beginning, acid-base theory, and you were asked to fill in this chart with different views of acids and bases according to these two different scientists. First, we have the Arrhenius definitions of acids and bases, and then we'll look at the Bronsted-Lowry idea of acids and bases. Well, Arrhenius. The Arrhenius acids, this is what probably most of you are the most familiar with if you're thinking about acids. In Arrhenius acids, we define acids as things that have the hydrogen ion. In Arrhenius bases, we define that as anything that has the hydroxide ion. So the hydrogen ion and the hydroxide ion, acids, bases. Oh, I should have made this in blue so that it would match all of the rest of the things that we have done in acids and bases. So I'm going to switch a color here so that I've got enough blue. So you know what? I'm going to put an OH here in blue just so that we have it. All right. For Bronsted-Lowry. Bronsted-Lowry doesn't talk about hydroxide at all. It only defines acids and bases in terms of hydrogen ions. For acids, a hydrogen ion donator. So if something can donate a hydrogen ion, it is a Bronsted-Lowry acid. In a Bronsted-Lowry base, it is something that can accept hydrogen ions. So in Bronsted-Lowry, it all has to do with whether you're going to donate or accept a hydrogen ion. Whereas with Arrhenius, we have a substance that has a hydrogen ion and then a substance that has the hydroxide ion. So let's take a look at number 2. Identify the acid base, conjugate acid, conjugate base, etc. for the following reactions. In whose theory do we have conjugate acids and conjugate bases?
I'm not really sure.
So, to begin with, if we're talking about conjugate acids and conjugate bases, we are talking about Bronsted-Lowry. Arrhenius doesn't discuss conjugate acids and conjugate bases. That's Bronsted-Lowry, because in Bronsted-Lowry, acids and bases donate and accept hydrogen ions, which means that they are forming conjugate acids and conjugate bases. So let's take a look at these equations. Now, what I find is very useful for each one of these is to take a look at each one separately and find its component on the other side of the equation. So if we take a look at HPO4 minus 2, and let's go to the other side of the equation. Well, here we have H2PO4 with a minus 1. So this thing became that thing. Well, here I have one hydrogen ion. Here I have two. So this thing actually accepted a hydrogen ion to become this. Since it accepted a hydrogen ion, well, let's look up here. Hydrogen ion acceptor. So this is going to be my base. Well, take a look at the H2O, water. Water, well, that means that water becomes this guy right here. So H2O becomes my OH negative. So it lost a hydrogen ion. Since it lost a hydrogen ion, that would be my acid. Well, if we go to the other side, acids become conjugate bases, and bases become conjugate acids. So if it was a base over here, it's a conjugate acid over here. If it's an acid over here, it's a conjugate base over there. So let's look right over here at this next one. HSeO3 negative. Well, let's take a look over here and find what must that be. Okay, here's the SO3 negative, but it's -2 because we have lost a hydrogen ion. Well, since this donated a hydrogen ion, that makes this the acid, and since this is an acid, that makes this our conjugate base. Well, H2O becomes H3O. Well, we've got one more hydrogen here than we did over here, so H2O accepted a hydrogen ion. Since it accepted a hydrogen ion, it is a base. Well, bases become a conjugate acid. All right, so whenever you deal with acids and bases and conjugate acids and bases, if you hear the word conjugate acids and bases, we're talking about Bronsted-Lowry. Now notice also, the conjugate acids and conjugate bases are both on the right-hand side of the equation. They're not on the left-hand side. They're not on the reactant side. They're on the product side over here. So our conjugate acids and conjugate bases are always on the product side. All right, so let's move on down to number 3, where it says label the following as an Arrhenius acid, an Arrhenius base, or neither. Well, let's remember that our definition of Arrhenius acids and bases. An Arrhenius acid has a hydrogen ion, and an Arrhenius base has the hydroxide ion. So let's take a look at these and then underline the part that seems to match. So, magnesium hydroxide. Well, that's simple. Look at there. There's our hydroxide. We see a hydroxide, so this must be an Arrhenius base. B. HBr. I see an H and of course bromine. So hydrogen bromide, and of course if it's an acid it would be hydrobromic acid. I see, well, that's an acid, but there's what makes it an acid right there, so this would be an Arrhenius acid. B or C, sodium hydroxide. Well, I'm going to have to get my blue pen back out again. There's my hydroxide. So, hydroxide, that means that it's an Arrhenius base. This next one, HCH3COO. Well, if you look on the back of your periodic table where our polyatomic ions are, what you will see is that CH3COO is acetate. So we put it together with the H, that means it's acetic acid. So there's our H, our hydrogen ion, so this would be an acid. So if you're looking for Arrhenius acids and bases, go through, underline. Do you see an H? or do you see an OH? The OH, of course, has to be together. And this has an OH in here too, but the O and the H, we're looking at that together. All right. Let's look down here. What is another word for a basic substance? Well, let's think back to our periodic table. Those first two columns on the periodic table had words like alkali metals, the alkaline earth metals. There's our word. If it's a base, we refer to it as being alkali. Explain why water is considered to be amphoteric. Well, we have to look up, make sure that we know this word amphoteric. If you don't remember what that word meant, go back and take a look at the very first PowerPoint for this particular section. And you had the definition of the word amphoteric. Amphoteric means that something can be both an acid and a base. So, water is considered amphoteric because it can act as an acid, but it can also act as a base. So if something can act as an acid and act as a base, then what you have is something that is amphoteric. All right, moving on down to acid and base properties. This too was on that very first PowerPoint that we looked at, or that we were able to see in this particular section. Define an acid and base indicator. Well, an acid and base indicator, if you recall, is a substance that changes color based on whether it's placed in an acid or a base. Since we can sort of attach a number to this, but the test itself is referred to as being qualitative because the test itself doesn't give you a number. We can go back and assign a number to it, but in order to actually have a quantitative measure, we have to have a pH meter, a digital pH meter. So, a substance that changes color based on whether or not you have an acid or a base. So it's qualitative. List the acid and base indicators that we learned about in this unit. Well, most all of us learned that we have litmus paper. And remember, with litmus paper, you actually had blue litmus paper and you had red litmus paper. So you have two different types of litmus paper. You also had pH paper. pH paper, it's another type of paper, just like litmus paper, but the pH paper, you don't have two different types. The pH paper is simply going to change color based on, it could go acid or base. Litmus paper can test acid or base too, and we'll take a look at that in the down at the bottom a little bit further. You may or may not, in your class, talked about universal indicator, which is not a paper. It is, but it works in the same principle with pH paper. It is a liquid. It's a liquid that changes color based on pH. And then we all learned about phenolphthalein. It's such a fun word to say, phenolphthalein. Okay, phenolphthalein is an acid-base indicator. So you probably learned about 3 of these at least. Not everybody talked about universal indicator, but it acts just like the pH paper. All right, chemical properties. The chemical properties of acids include being able to react with. Now remember, these are chemical properties, so these are talking about what it can react with. Well, if we think, to start with, chemical properties, we know that an acid is going to react with a base. We know that an acid will react with metal. And we know that an acid will react with carbonates. That would be things that have the CO3. So like limestone and marble, things like that. List 4 chemical properties, 4 physical properties of acids. Now, before we go to that, any idea why we didn't put down here chemical properties of a base? Well, when we start thinking about the chemical properties of a base, what will it react with? Bases will react with acids. Bases don't react with metals. Bases don't react with carbonates. They will react with acids. So let's list chemical or physical properties. Physical properties of our acids. Well, if you've had those wonderful sour candies, you have tasted an acid. That is citric acid. And of course, sour candy, so it's sour. So acids taste sour. Acids are electrolytes. They will conduct electricity. Okay? They will conduct electricity because they are electrolytes. Acids are soluble in water. And acids can burn you, obviously. Okay, acids can burn. Look at then the physical properties of our bases. Bases, if it's a base that's safe to taste, think about a lot of plants, plant bases that you might put onto things. Bases taste bitter. Bases are also electrolytes. Bases are soluble in water. They can burn. And then there's another one that's in here for bases that's different from acids. Bases tend to feel slippery. Okay? If you've ever put your fingers into bleach or a strong ammonia solution, you felt that they probably feel pretty slippery. Bases tend to feel slippery. Well, one of the things that you come into contact with on a regular basis that is a base would be soap. It's not the reason that soap is slippery, but soaps are bases. Okay, so let's move along down. Number 9, which of the following will HNO3 in an aqueous solution react? Well, let's decide first. Do we have HNO3 in an aqueous solution? Is this an acid or a base? Well, if I look up here, I can't tell if it's going to donate or accept anything because so I don't really know about that, but I can look straight away and see that it has a hydrogen. So that's a hydrogen along with a polyatomic ion. So this is going to be an Arrhenius acid. So that's the first thing I do. I've identified that this guy right here is an acid. Well, let's look through here and think, what will an acid react with? You want to know what it's going to react with? Well, I just listed up here all the things that it will react with. Bases, metals, and carbonates. Well, let's take a look. A, KOH, potassium hydroxide. Well, I see an OH here, so that makes this a base. So, will an acid react with that? Yes, it will. So, I'm going to circle potassium hydroxide because it will react with that. B, calcium carbonate, CO3. If you look on the back of your periodic table, you will see carbonate. Well, there you go. Acids react with carbonates, so I need to circle that. Over here, zinc. Well, is zinc a metal or a non-metal? Left-hand side of the periodic table, it's a metal. Therefore, there you go. Potassium, also a metal, so there you go. So it turns out that this acid, which is nitric acid, will react with all of those. Number 10, which of the following would sodium hydroxide react? With which of the following would sodium hydroxide react? Well, here I'm looking at OH, which makes this an Arrhenius base. So now let's look back up here. Bases will react with, we didn't put it up here, but I told you when we were looking at that bases will only react, and if you look back at your notes from that particular PowerPoint, bases react with acids. So what we need to do here is find the things that are in this group that are acids. A, HCN. Well, that's a hydrogen ion right there up in the front, so that's an acid, so it will react with that. B, KOH. Well, KOH has the same thing that this does, so that's a base, so it will not react with B. C, calcium carbonate. CaCO3. Calcium carbonate. That is a carbonate. Therefore, will bases react with carbonates? Nope, it will not. H2S. Well, I see my hydrogen ion right there, so that makes this an acid. Will bases react with acids? Yes, it will. And of course, H2S, that would be hydrosulfuric acid. So, there we go. Looking at number 11, what color does phenolphthalein turn in the presence of an acid, a base, or a neutral solution? Well, phenolphthalein doesn't do very much in an acid or a neutral solution, but phenolphthalein in a base turns pink, bright pink. In a neutral solution, it stays clear. And in an acid, it typically will stay clear. Sometimes you might see a little milky color for a second or two, but typically it stays clear. Number 12 says, what color does litmus paper turn in the presence of an acid, a base, or a neutral solution? Well, remember that you have blue litmus paper and you have red litmus paper. In an acid, blue litmus paper turns red. Red litmus paper stays red. And in a neutral solution, I guess I should put that down here too, in a neutral solution, let's go base, neutral. In a base, blue litmus paper stays blue, red litmus paper turns blue. In a neutral solution, blue litmus paper stays blue, red litmus paper stays red, now, what would you do if you put a piece of litmus paper, red litmus paper, into a solution and it stayed red? There are two possibilities. Either it's neutral or it's an acid. So, if you test something and it stays that color, blue stays blue or red stays red, the only way to know if it's neutral or an acid or a base is to test it also with the other color. So, because if I stick a piece of blue litmus paper into a neutral solution, it's blue, and if I stick it into a base, it's also blue. So, if I stick blue in there and it's blue, I have no idea, is it neutral or is it a base? The only way that I could tell then for sure is to use red. So, if I were going to fill this out the way that it's written here, if I were to fill this out the way that it's written, in an acid, litmus paper is red. In a base, litmus paper is blue. Now it may turn red or turn blue depending on which one it is. And in a neutral solution, the blue litmus paper stays blue, the red litmus paper stays red. So I'm going to write here that there's no change. So in a neutral solution, you will not see a change with litmus paper. All right, presto changeo, next page. Number 13. Examine this data table and fill in the blank spaces to the right with the appropriate term. All right, so what we want to know is what's happening with each one of these things. What do we have going on here? All right, if we have unknown sample A, red litmus paper stays red, blue litmus paper turns blue, and phenolphthalein stays clear. Well, phenolphthalein stays clear in both an acid and in a neutral solution. Blue litmus paper only turns red if there's an acid. Red litmus paper stays red in an acid, so all of the data here indicates that this would be an acid. Unknown B, it's neutral, and so I've got to fill in everything here. Well, what does red litmus paper do in a neutral solution? Well, both colors of litmus paper stay their natural color in neutral solution. They don't change. So red litmus paper stays red. Blue litmus paper stays blue. And phenolphthalein stays clear. So these three pieces of evidence together tell me that this is a neutral solution. All right, then finally unknown C. Red litmus paper turns blue. Well, red litmus paper only turns blue in a base. So this is probably a base. So let's see if the rest of our data, the rest of the evidence points in that direction too. Blue litmus paper stays blue. Yes, it stays blue in a base. It also stays blue in neutral, but that's red. Phenolphthalein. Phenolphthalein turns pink. Phenolphthalein only turns pink when you have a base. So we have three pieces of evidence all pointing to the fact that this is a base. Part A, or letter A, looking at this chart. Which of the unknowns would have more hydrogen ions? Well, which of these three things, acid, neutral, or base, is associated with a high number of hydrogen ions? That, of course, would be an acid. Which of the unknowns would have a pH above 7? Well, if pH is above 7, even though we haven't done that in the review yet, anything that's above 7 is a base in pH. So, if it's above 7, it's a base. Well, oh, sorry, which unknown? Well, which unknown was an acid? That would be unknown A. And then which unknown is a base? That would be unknown C. All right, so moving on to pH and pOH. Here we have to fill in, do we have equal to 7, less than 7, or greater than 7? Well, let's think about our pH scale really quickly. We have 7 in the middle, 0 here, 14 here. Anything less than 7 on pH scale is an acid, becoming more and more acidic as you go this way. And on the pH scale, going from 7, anything above 7 is a base. So above 7 base, below 7 acid, and if it is 7, then it is neutral. Notice that I've colored this in green. All right, so let's see if we can figure out what these answers are. Hydrogen ions equal hydroxide ions. Well, if those two things are equal to each other, that means we have a neutral solution. One thing's not more than the other. It's a neutral solution. So, neutral solution would be equal to 7. hydrogen ions greater than hydroxide? Well, if we have a high abundance of hydrogen ions, that means we have an acid, right? Well, which one of these things indicates acid? Well, it's everything on that's less than 7. So, less than 7. If our hydrogen ions are less than hydroxide ions, that means you've got a higher abundance of hydroxide. Well, high abundance of hydroxide means base. Well, if you look over here, anything greater than 7 is a base. So this would be greater than 7. Well, look at D, E, and F about what's going on let's see, we've got what happens to the pH when a weak acid reacts with a strong base. Well, this has to do with weak and strong acids and bases, even though, again, that's going to be on tomorrow's part of the review, but we should know what happens to the pH when we react these things together. Well, a strong base, that's going to be way down here, and a weak acid. Weak acids don't do a lot of dissociation, so you're not going to get a great deal of dissociation, a lot of hydrogen ions in that. So a weak acid and a strong base is still not going to be neutralized. It will be a little bit greater than 7. So if you have a strong base, it's going to be greater than 7. If you have a strong acid and a strong base, well, in looking at neutralization, strong acid, strong base will completely neutralize, and so you have 7, as long as you have equal molarities of both and equal amounts. The last one, you have a strong acid and a weak base. Strong acid means that it's way down here. Weak base means that it's here. So we're still going to end up with something that's acidic, but it's not going to be quite as acidic as that strong acid. So it's still going to have a pH that is less than 7. For these things right here, look on the neutralization PowerPoint. Look on the neutralization PowerPoint and you'll see a chart that goes through and talks specifically about what happens when you have a weak acid and a strong base and a strong acid and a strong base and a strong acid and a weak base. Now, when you have both a weak acid and a weak base, that could vary. It depends on which is the stronger or which one will dissociate more, and being able to calculate that is not within this course, so we won't do that. All right, so look at 15. We have an unknown substance, and we've got to tell if it is acidic, alkali, or neutral. Not really sure why we decided to use alkaline here, but we know it's a base, and so we'll use it. Unknown A has a pH of 6. Well, let's look back up here at my pH scale. If it's 6, it's down here, so that's an acid. Unknown B has a pH of 8. Well, it's a pH of 8, so that's on this side of 7. So that would be a base. Oh, I got to use the word alkaline. Unknown C has a pH of 10. Well, 10 is greater than 7, so again, we're alkaline. A pH of 1. Well, 1's way down here as opposed to 7, so that's going to be an acid. Unknown E is a pH of 7. Well, 7's right in the middle, so that would be neutral. Which sample has the most hydrogen ions? Well, if it has the most hydrogen ions, it's going to have the lowest pH. So let's look up here and find which one has the lowest pH. That would, of course, be this one. So, which has the most hydrogen ions? That would be unknown D. Which sample has the most hydroxide ions? Well, hydroxide, that's a base. So which one of these is the most basic, or the furthest away from 7 going towards 14? That would be this one with a pH of 10. So unknown C. look at letter C here. Compare the number of hydrogen ions to the number of hydroxide ions in unknown E. Well, unknown E is a neutral, so its number of hydrogen ions should equal the number of hydroxide ions. So they are equal to each other. So hydroxide ions and hydrogen ions are equal to each other in unknown E. All right, each pH unit is based on on what? Well, in the PowerPoint dealing with pH and pOH, we learned that as you go up one number in the pH scale, that's the equivalent of 10 to that particular power, looking at the hydrogen ion concentration, because pH itself is the negative logarithm of the hydrogen ion concentration, which you don't need to worry about the math with that. But remember what we did. If we take the pH of one and we subtract the pH of the other, whatever number we get there, we use that as our power of 10. So each change in pH unit is based on what? Well, it's based on the power of 10. Okay, powers of 10. So, like pH of 1 would be 10 to the first power, 10 to the second, and so on. Okay? So, compare the strength of unknown A to unknown D. Unknown A has a pH of 6. Unknown D has a pH of 1. 6 minus 1 is 5. So 10 to the 5th power. Well, 10 to the 5th power, that is 1 followed by 5 zeros. 1, 2, 3, 4, 5. So 100,000. So unknown D is 100,000 times more acidic than unknown A. Compare the strength of unknown B to unknown C. Well, unknown B is 8 and unknown C is 10. 10 minus 8 is 2. So that's 10 to the second power. So 10 to the second power is 1 followed by 2 zeros, so 100. So C is, well, if we're looking at acids or whatever, we can go in either direction. B to C. Unknown B is 100 times less basic than C. Or you could say that C is 100 times more basic than B. All right, let's go. We'll go ahead and do number 16 here, so that means that we'll start with number 17 in part 2. Describe the properties of a strong acid or base and the properties of a weak acid and base, and this will set the picture for part 2. Properties of a strong acid and base. If we remember, if it's a strong acid or base, it is going to dissociate completely. Dissociate 100%. The ions come completely apart. Because it dissociates 100%, it is a strong electrolyte. That means it will light up that light bulb a lot. Okay, got a bright light. And you have 100% ionization. All those things work together. It dissociates 100%, which means you have 100% ionization. Everything in there is ions, which means that you've got bright light. It's a strong electrolyte. Weak acids and bases. This dissociates less than 100%. How much less depends on how the particular acid or base, how weak it is. It's still an electrolyte, but it's a weaker electrolyte, which means that it's going to light up the light bulb not quite as bright. It's going to be dim. And you have, of course, less than 100% ionization. And there you go. That's part 1. We will pick up with part 2 tomorrow.